Now let's continue our discussion in the chapter of probability. And we discussed there are two events be independent if the occurrence of one event has nothing to do with the occurrence of the other. And so if two events A and B are independent, we have P of A and B equals P of A times P of B. On the other hand, there are a lot of things in real life that are dependent. So the definition of dependent is the opposite of independent. Namely, if two events are not independent, they're defined as dependent. So let's take a look at this example. So suppose the electrician puts two new fuses into the fuse sockets in the new house. So he has the box of 4 fuses. He thinks 4 of them are all good. So this is what he thinks. However, the reality is there is one that's bad. So there is a good one, there is a good one, and there is a good one, and then there is a bad one. And of course, he doesn't really know which one is bad because they all looked alike. So when he put the 2 fuses from the box into the sockets, what is the probability that both will be the good ones? So let A be the event that the first one is good. And then let B be the event that the second one is also good. So we need to find the probability of A and B. Well, notice that in this case, you cannot just use the probability of A times the probability of B because these two events are not independent. Namely, whether you choose A or whether you choose the first one being the good one or bad one affects the probability of the second one. So think about it. If you choose the first one being the good one, then the chances for you to choose the second one also being a good is 2/3. On the other hand, if you choose the first one being a bad one, then the chances for you to choose the second one being a good one is actually 1. So in this case, first of all, let's consider what is the probability of the first one being good. So that one is 3/4. So that's the probability of the first one being good. Now, assuming that one good one has already been chosen, now we want to also the second one being good. So now this is, you see here, 2 good ones left with 1 bad one. So it's 2/3. So the answer is calculated by 3/2 times 2/3, which simplifies to 1/2. So, and this would actually give you a general rule, namely the probability of A and B, assuming that A and B are dependent, is calculated by P of A times a second term, which is P of B, given that A occurs. So you see here, the first term, 3/4, is P of A, the first one being good, and then P of B, the second one being good, assuming that A occurs, assuming they already taken a good one out from the box, then the second one also being good is 2/3. So that's how we calculate the dependent event in B. And of course, let's just briefly recap what the elementary events are. And the probability of events consists of sums of the probability of its elementary events. For example, if you want to find out, if you just draw a random card from a deck of 52 cards, and then the event ace is composed by putting together the 4 elementary events. There are 4 types of aces, and each one of them has the probability of 1/52. So the probability of ace is equal to the sum of 4 copies of 1/52. That is 4/52. Now let's talk about the combined event A and B. Well, when we say A and B, we have 2 events, A and B, they may or may not have anything in common. So like, for example, on the graph on the left, you see here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points. And 2 of them are neither in B nor A. And then 3 of them are in A, but not in B. 3 of them are in B, not in A. And 2 of them are in both A and B. So when we say A and B, we mean the common elements of A and B. So there will be 2 elements in the middle. On the other hand, if you have this scenario, you have 2 events, C and D. The right one is called D. And then you see they have nothing They have nothing in common. So in that case, C and D would become impossible. It's kind of like saying an animal being both a cat and a dog at the same time is impossible. So let's take a look at this example. Suppose that a department store holds a clearance sale. This is the same scenario set up as we have seen before. And two boxes, one box with the seat cushion. So there is a seat cushion and with the 3 white ones and 4 blue ones. Of course, you don't really know which one is which unless you look at it. And then 1 red one. So this is the seat cushion. On the other hand, you have back cushions. So for the back cushions, you have 2 red ones as well as 5 green ones. So now let's take a look at M be the event that a pair has a white seat cushion, and N is the event that the back cushion is red. So here, M, if you just close your eyes and randomly choose 2 cushions, M is what you choose from the seat cushion being white, and N is the back cushion being red. Well, now in this case, M and N are mutually exclusive. I mean, are mutually independent. I'm sorry, are mutually independent. Whether you, whatever color you choose to the seat cushion has nothing to do with whatever you choose from the back cushion. So in this case, P of M and N is simply equal to P of M times P of M. P of M is equal to 3/8 because of 3 white cushions out of 8 a total, and P of N is 2/7. So the final result is 3/28. Again, this comes from the independent events. On the other hand, let's just use the same. Let's use the same setting, but let's change this M and N a little bit. M being the event that the seat cushions and back cushions are the same color, so you have to choose the same color, and N be the event that the seat cushion is white. Well, I want you to think about this for a minute. Can you possibly choose a white seat cushion, yet you have the back cushion being the same color as white? The answer is no, that's not even theoretically possible. So in this case, M and N has nothing in common. So, or in other words, in this case, we say that the probability of M and N becomes 0. So the solution is 0 because that's impossible. So when we in real life, we use the word A or B. Sometimes we mean inclusive, sometimes we mean exclusive. By inclusive, I mean when we say A or B, we automatically include all the elements inside both A and B. Let's think about that. Suppose that let's say you're applying for a job, and if a job qualification says that you must have a 3 years work experience or a master's degree in this field. So what if your applicant has both a master's degree and a 3 years experience? And the answer is that's not a problem. Everyone understands that when they say the qualification is 3 years of experience or a master's degree, there's nothing wrong with having both. And if you have both, that's great. And you don't have to eliminate that applicant just because he has both. And on the other hand, in some of the other real life scenarios, when we say A or B, we mean it's either A or B, but not both. One example would be, where do you want to go for lunch? Do you want to go to KFC or McDonald's? Well, normally when people say phrases like that, they mean either one or two, but not both. We don't want to both go to KFC and McDonald's. That's not going to work very well. Well, it could, but usually that's not what people mean. Here, we have to make a convention what we want to believe as we study mathematics, because we don't tolerate any ambiguity in mathematics. Here is the convention. Whenever we say A or B, we always mean the inclusive or in mathematics and statistics. Or in other words, when we say A or B, an element could be in A alone, B alone, or in both A and B. So all these 1, 2, 3, 4, 5, 6, 7, 8 elements are all in A or B. Like in the second example, the C or B consists of those 7 elements, as there is no elements in both A, C, and D. Now let's take a look at the next example. So suppose we have a family with 3 children, and what is the probability that this family has a girl first, or a boy third, or both? Well, here the question makes it crystal clear that we like the inclusive or, even though, even if this or both phrase is missing, we still mean the same thing. Now, to look at this, we consider all the possible combinations. They're actually not a whole lot. There'll be 8 of them. So you can have a boy first, and followed by a boy, and then a boy. 3 boys. Or boy, boy, girl. That's another combination. And boy, girl, boy. And also boy, girl, girl. So those are the possibilities with the boy first. And now you have a girl, boy, boy. Just basically copy these 4, but change the boy to girl. So it's girl, boy, girl. And then girl, girl, boy, and 3 girls. So you see, these are the 8 possible elementary events. Each one of them is equally likely. So now let's take a look at which ones should we choose. It's either a girl first, so I'm going to choose this one, and this one, and this one, and this one, or a boy the third. So I'm going to choose this one and this one, and also this one, but we choose it 2 times. That's okay. We don't really count it 2 times. This case is included in the both scenario. So now if you count, you have 1, 2, 3, 4, 5, 6. You have 6 possible scenarios out of 8 elementary events satisfy this condition. So the solution is 6/8 or 3/4. And if A and B are mutually exclusive, then of course, when we say A or B, that means either in A alone or B alone. And therefore, but not both, because there's nothing in both. And therefore, you have P of A or B equals P of A plus P of B. And well, I do want to mention that whenever you see a formula in this course or in any math course, don't just write down the formula without understanding the context. Here, this formula is true under the assumption that A and B are, under the condition that A and B are mutually exclusive. So this is the condition for that. All right, so let's take a look at this chair example again. And again, we have the same combination of chairs, the cushions. And now M being the event that the seat and back cushions are the same color, and N being the event that the seat cushion is white. We actually computed P of M, and before P of M is, well, P of M means the same color, so the only same color is red. So it's 1/8 times 2/7. So this is 2/56, or 1/28. So this is P of M. And then we also know that P of N means the seat cushion is white. So the seat cushion being white is 3 out of 8. So this is the probability. Now, you see here, we have M and N are mutually exclusive. So here, M and N are mutually exclusive, which means they have nothing in common. So P of M or N can be calculated by P of M plus P of N. So this one equals 1/28 and plus 3/8. And I'm not going to insult your wisdom by showing you how to do this calculation. And eventually, your result is going to be 23/56. So that's how you calculate the probability of P2 mutually exclusive elements. And now, what if they are not mutually exclusive? We have the general addition rule. What this means, think about that. If you have 2 events, they are not necessarily mutually exclusive. For example, this is A, and then this is a B. And, well, in the middle, this is what we call here, this is in the middle, is what A and B. Well, think about that. when we say A or B, that means the whole thing is A or B. Okay, so this is A or B. Now, why that is equal to right-hand side? If you look at P of A, so that's basically the first circle, plus P of B and second circle. Well, but notice that you actually added this thing twice. You actually added the thing twice. So you have to subtract it from the result, and therefore is the P of A plus P of B minus P of A and B. This is the general addition rule. Will give you P of A or B. So let's take a look at this example. Suppose we have a testing machine scores a concentration of a chemical, and the blood sample is 1, 2, 3, 4, 5, 6. So those are basically 6 different results. And for the healthy people, those scores are just likely, equally likely. So it's kind of like rolling a die. And however, with people for a certain disease, and then it's more likely to get number 6 instead of the other 5 numbers. So we want to make sure the machine works properly. So the technician scores 2 healthy people. If either one is a 6, and then when the technician need to recheck the settings of the machine, because the technician somehow believes that seeing a 6 for 2 healthy people is not likely. So if I see either a 6, and then we need to reset the machine. So what's the probability that this is basically unnecessary? The machine is really working the way it is, but we still recheck the machine. Or in other words, assuming that the machine is good, what's the probability for 2 random people and using the machine shows either a 6? So now here, the probability, let's look at this. A being the first one, first people has a 6, okay, and B be the second people. The second person has a 6, and now we want to do P of A or B. So that is equal to P of A and add P of B. Now the general addition rule is minus P of A and B. So notice that in this case, A and B are not mutually exclusive because they can both be 6. That's possible. They're not likely, but it's possible. So in this case, we have P of A, of course, that's 1/6, and plus P of B, that's 1/6, and minus P of A and B. Well, notice that A and B are mutually independent, and therefore the probability P of A and B is really just P of A times P of B. So it's 1/6 times 1/6. So at the end of the day, you find the result is equal to 11/36. So that's the probability for you to see at least 1/6 among these 2 people. That's about a little bit under 1/3. All right, let's say a few words about a complement. If A is an event in the sampling space, and the complement is just anything that's not in A. So we denote by A bar. So here the properties are more or less clear, and P of A or A bar is equal to 1. An element either belongs to A or not belong to A. And P A of A and A bar is 0 because you can't have an element belongs to A and not belong to A at the same time. And so, for example, find the probability that a card from a 52 card deck is not an ace. Well, we just simply need to find the probability of an ace and then use 1 to subtract that number. So the answer is 1 minus 1/13, which gives you 12/13. Thank you very much for watching. I will see you in the next video.